We're going to take the prepared data from the chemical toxicity dataset and load that into my Interpretable machine learning app that I've coded up using the R programming language. But first, we're going to set up the mode and say classification, because we're trying to predict a class, yes or no, whether the drug will be toxic. Okay, so now we have the training data in the training input and the holdout data, 5 of the chemicals that we do not include in the training data in the holdout set. We've decided to use 30% of the training data as a evaluation or test set, and now we'll just wait for the models to train. Now that the models have finished running in the background, in this case for our classification problem, an XGBoost model and a random forest model, we can evaluate how they did on the test data, the 30% held out from the trained data. With these metrics, we're looking for higher numbers representing better performance, and we can see in this case that the random forest had the higher area under the curve, AUC, at 0.747 relative to XGBoost 0.679 on the 30% held out from the trained data. So since that's the case, we are going to switch over to random forest as our model choice and hit download predictions. In this interactive studio, we can interpret the machine learning model, in this case the random forest model, that was the best at classifying whether a given chemical was going to be toxic or not. Starting off, we can see feature importance ranked by their importance to the model here. So aromatic count, the count of aromatic instances inside the chemical was the most important, followed by count of nitrogen atoms, count of oxygen atoms, molecular weight, ring systems, carboxyl functional groups, charges, and various other functional groups. We can also get the breakdown of a given prediction. So the 5 chemicals we use as our final holdout to predict whether they were going to be toxic or not are here, 1 through 5. And if you look in the blog, you'll see the first one, number 1, was non-toxic, and then the final 4 ended up being toxic. We can see that the baseline probability that any given chemical is toxic is about 0.514 in this data set, and from there, the input variables are going to determine the prediction of a given chemical and its probability of being toxic. In this case, for chemical number 1, it seems less likely than the baseline to be toxic at a 0.47 probability, or about 47% chance, relative to the 51% chance by random chance up there. We can change chemicals and see how the other ones fared in their predictions. We know that the final 4 were all toxic, and we can see a prediction here for number 2 being higher chance than baseline of being toxic, so that makes sense. Let's see how the other ones did. Higher than baseline chance. Higher than baseline chance. And finally, number 5. Again, higher than baseline chance. So that shows that the model is doing pretty good at separating toxic from non-toxic chemicals. And we can see the explanation here of how negatively with the pink or positively with the green, a given variable for a given chemical influences its final prediction. We also have other tools we can use in here, like average target versus feature, and we can see how various variables, let's check the most important one, aromatic, and how it relates to the chance of a target being toxic. We can see there is kind of a horseshoe-shaped response here, where in this middle region, it leads to a higher probability of there being a toxic chemical, and at the extremes of 0 aromatics versus 5 aromatics, there seems to be a lower chance of being toxic. This is just to demonstrate some of the capabilities of this interpretable machine learning output. You can, of course, change through all the different input variables that we have considered here, see how they relate to the response on their own. Of course, our model is a little more complicated, nonlinear and conditional than these simple plots here. But if you are trying to separate out an individual variable, how it relates to the response, this is pretty nice for that. And there are also various other ways you can look at how the input variables influence the chances of a given chemical being toxic.